Okay, good afternoon, everyone. Welcome to the HAO Colloquium. Today, we are very happy to have Dr. Jia Yue to give a talk, and I know he's an old friend of many of you here. But even so, let me still give a brief introduction of Dr. Yue. Sorry. Well, I think this is my first time chair the colloquium for this summer, so I need some time to get into my role. Okay, Dr. Yue is the Ionosphere, Thermosphere, Mesosphere modeling lead scientist at the NASA's CCMC, Coordinated Community Modeling Center in the Space Weather Lab. He received his PhD degree in electric and computer engineering from Colorado State University in 2009. And Jia has authored and co-authored over 160 journal papers, articles, and book chapters in mesosphere and thermosphere physics. His research interests include fundamental mesosphere and thermosphere physics, vertical coupling between the low atmosphere and geospace, long-term changes in the upper atmosphere, and optical remote sensing. He served on the AIM, and the Time Science teams. And he was also recently appointed as a PI of the SABRE mission. Congratulations, by the way. He received the Scott Stepp Young Scientist Award and the NASA Robert Goddard Award in Science. And he's now a associate editor for JGR Atmospheres. He is also actively involved in citizen science as a co-I of Spiritacular. And today he is going to talk about the wizard of OZ thermosphere physics revisited. So please take it away, Jeff.
Yeah, thanks for the introduction, Don. I want to be able to see any of your faces. So stop me if you have any questions. Like Don said, I've been the old friend, and also I say the ASP postdoc from HAO many years ago. So I'm not familiar face to many of you. I would first especially thank Wenbing Wang. Actually, this talk was inspired by a recent book chapter in Encyclopedia, and also Dong and Haonan at HAO and Jack Wang helped a lot on this book chapter. And it's based on the previous version. The first version was written by Ray Robo. And the second version was by Ray and Stan Solomon. So this is the third version. And I've over the so many years, I've had very fruitful discussions with many scientists in and out of NCAR. So this is the outline. I want to briefly review the history and also basics of thermosphere physics and the recent progresses in thermosphere physics that particularly contribute to the understanding of the thermosphere mass density that is the primarily important for calculating the satellite drag. And the physics models, how the thermosphere physics is included in the physics models, such as YCOM-X and others, and also related to operation. And imagine in the future, so through the lens of GDC and dynamic on the horizon. So how's that gonna benefit this field? Okay. Yeah. So can you see my cursor here?
Yes.
Okay. So yeah, so this is inspired by this book chapter that Wenbing and I wrote, and it was published recently. So we feel kind of it's time to review the progress and also I learned a lot of just basic physics from Wenbing. So why this is timely, as you know, there have been some very good ionosphere textbooks, for example, by Mike Kelly, Shank, and Nagy, but there haven't been a lot of comprehensive thermosphere books or reviews. Why and up to date thermosphere physics review is needed now. First of all, there, as you know, there are over the recent years have been the magnitudes more satellite launches when the rocket launch becomes affordable. So there are more orders of more objects in the thermosphere, in the LEO, the low Earth orbit. So the need to simulate or even forecast thermosphere mass density have never been, overarching like before. People can use empirical models, but also another option is physics models. So if people want to use the physics model, the first thing to make sure that the physics is correct in the model. And another thing is the ionosphere basically is within the thermosphere. So any of the thermosphere neutral dynamics and also the neutral plasma coupling that feedback to the ionosphere and make the ionosphere modeling also more accurate. And the buzzwords right now is the space weather everywhere. So understand the impact of space weather, space exploration, the ionosphere, thermosphere hasn't never been important like right now. So this is just artwork from the EOS article by Bronsma et al. Shows the explosion of space objects, whether it's satellite or just debris in the thermosphere. So we are so get out the the ivory tower. We want to see what's the thermosphere in the mainstream media, right? So what the public cares about the thermosphere. So there are different articles over the recent years I found online. The Wall Street Journal cares about the tourism of the upper ionosphere by Virgin Galactic. The CNN reported the unusual upper ionosphere shrinking. I talk about that later. The USA Today that the hot temperature in the thermosphere would not melt the spacecraft, yeah, so it's just what the thermosphere's view in public. Then this is my view of the thermosphere. It's like a apartment, the 30th apartment in Manhattan. How much air in the thermosphere depending on how much air in the 29th floor. So the composition is largely coming from below the mesosphere or the lower thermosphere. So anything happen below, they're going to impact the thermosphere. You can imagine there are two stuffs in the two sides of the room. That's the two polar regions. During geomagnetic storms, it could heat up the thermosphere. You can think of the air conditioner as solar radiation can control the entire room. The basic thermal structure of the thermosphere or the atmosphere. So the thermosphere is where the temperature rises. To get the name from this, and this is the mesopause, which is the coldest place on Earth. And the thermosphere is very sensitive to the solar cycle, the UV radiation. So I think this plot is from NCAR. So during solar maximum, the temperature is hundreds of degrees hotter than during solar minimum. And this is what the upper ionosphere look like from the satellite or International Space Station. So this is the time satellite. It's basically dark there because there's very little particles to really scatter light. So it's all dark. The composition, that's how a thermosphere is very different from the lower part of the atmosphere, because there's a lack of mixing, or you can call it molecular diffusion separation. The heavier molecules or atoms sort of descend into the lower part of the thermosphere, while the lighter molecule, or mostly atoms like atomic oxygen, helium, and hydrogen, they become the major species at higher altitude. So this is work done by also HAO. A group of scientists led by Wenbing, after adding the helium into the Thai GCM, they could lift the upper boundary to higher altitude and cover more LEO orbit used by more satellites. And this is included in the new version of Thai GCM. I should mention this. So trying to compare the thermosphere physics to the just conventional atmospheric science, well, the core is the same. Still need to solve the Navier-Stokes equation, but the mass equations have to be considered for different species, major species like oxygen, atomic oxygen, molecular oxygen, and nitrogen. There are some new forces comparing to the troposphere or even stratosphere. There's a very strong molecular viscosity added into the equation to remove the wind shears, and also the ion drag. So the collision between the ions and the neutral particles. So this is the equation. And for the thermodynamic equation, the Joule heating needs to be added in the high latitudes. So this is the equation for the Joule heating. So this is from 2016 paper that shows the balance of force in the thermosphere. The viscosity, you can see the dominating force is the pressure gradient force and the ion drag. So this is very different from the lower atmosphere. And there's a wind system that produced by Dong and Haonan. It shows the wind is blowing from at the higher part of the thermosphere.
Hey, Jack, sorry for interrupting. Yeah, I just want to clarify that this plots were made by Haonan, so I want to give him the full credit.
Oh, okay. All right. Okay, so this is from Wacom X. The warm, this red indicates warm region and the cold region, the daytime and nighttime. So in the upper part of the thermosphere, it's the wind is blowing from daytime to nighttime. In the lower part of the thermosphere because it is the tides that propagating from below, especially the semi-diurnal tides that could modulate the wind field. So you could see this kind of two peak structures in the local time or longitude. So it's more complicated in the lower part of the thermosphere. In the polar region, the ion velocity can sometimes be higher, faster than the neutral wind. So during especially geomagnetic storms or active periods, the convection drive this strong movement of ions, and that pushes the neutrals. So create this complicated neutral wind system in the polar region, and this can also propagate into high and into mid and low latitudes. One unique aspect of the thermosphere dynamics, unlike the lower atmosphere, is the wind changes composition. This is very different from the lower atmosphere. So imagine there's a hurricane here, but doesn't change the amount of oxygen from one place to another. The mixing ratio of oxygen is the same. But that is very different from the thermosphere. So you can see because mixing ratio of different species are very different, an upward wind would bring more molecules to the higher altitude, and also the oxygen, less air. So you can call it thermosphere hypoxia. So that any sort of the wind also modulate the abundance of oxygen. And this has been clearly observed by, for example, gold from the GAN 2023 paper, that during a geomagnetic storm that the gold O2 N2 ratio shows depletion in the polar regions. The history of thermosphere research, if we ignore the V2 rocket, the first, the early day post World War II V2, some rocket launches, there are two phases. The first one comes with the first arrival of artificial satellites, the atmospheric explorer and dynamic explorer. I believe a lot of scientists, especially the senior scientists, are sitting in NCAR and other places from those programs. The presenting models are the empirical models, like the AMSIS, coming from the heading. He was from NASA Goddard, and after he retired, Naval Research Lab took it over. Then Ray Robo at NCAR developed the physics models, TIE-GCM. Well, there are several phases, different versions, TIE-GCM, and also the CTIP from UK. Then 2000 marked the second phase. That's basically the time launched in 2001, and there's a series of other satellites like AM, ICON, and GOLD were launched. In the meantime, in 2000, the modern accelerometers were launched in several satellites like CHAMP, GOCHE, GRACE, SWAN, and GRACE-FO. And those accelerometers can quantify, can measure mass density in unprecedented accuracy. And the models are like updated AMSIS 2.0. John Emmert gave a talk at the CEDAR workshop recently, and the WICOM-X, that is the whole atmosphere model. another whole atmosphere model, 1MIPE. And also in the new age, the magnetosphere MHD model started to couple with the IT models like MAGE, developed by NCAR and APO, and also the one-way coupled SWMF and Keaton from Michigan, and the empirical model that digests all the accelerometer neutral density developed by Bransma. So that's and that's kind of the two phases we're talking about here. So those are the measurements of the remote sensing measurements in the stratosphere, mesosphere, and lower thermosphere. So those are the fleet of satellites. This is Malinczak's article. The focus is on the MLT region, but you can see the number of satellites were launched. And especially around 2000, that's been for 20 years, that has been a number of satellites taking measurement at the same time. But it's kind of, I talk about it later. It's kind of close to the end of this period, with all the satellites are near the end of their lifetime. And here's the left-hand side is accelerometer data, starting with CHAMP, then Goche, and also GRACE. And this Bransma article reviewed the distribution of the accelerometer mass density data. This part is from the Goche, which is was at much lower altitude, but the lifetime was short. It's about 3 years. Then the upper part was by CHAMP and GRACE. You can see that it's not only the local time, the measurement during very large extreme storms are very limited. And this limited coverage of mass spectrometer data also limited the performance of the empirical model during extreme events. So Wenbing and I put together this schematic of the physics involved in the thermosphere. It's very complicated. So Wenbing and I, we did a lot of back and forth. So there could still be some mistakes. The red arrows are the neutral ion coupling physics. You can see the ion drag or field aligned transport. And the right-hand side is more the ionosphere, the plasma density electric field ion drift. The left-hand side is the thermosphere, the neutral wind, neutral temperature, neutral composition. And the highlighted is mass density. So for a physics model, to get the mass density correct, you should have a lot of process correctly calculated. And the exchange of energy, the heating, the energy input from the solar EUV radiation, aurora, precipitation, the electric field from the magnetosphere, and also the cooling, the radiation cooling back to the space, the CO2 and NO. And from the lower ionosphere, the input of the wave dynamics, wave forcing, and also eddy diffusion. So it's a very complicated system. For the concern of satellite drag or neutral density, basically in most of the LEO altitudes, it's atomic oxygen density as a function of altitude, not pressure. So I think the first controlling factor is still the expansion or contraction, or following the heating and cooling by the ideal gas law. And just comparing the previous version of the flow chart made by Ray Robo in 1983, there are a lot of information already included, but there's something are not considered here. For example, the waves from below, and also the NO and the CO2 cooling, and that's why the Thai GCM doesn't have, for example, gravity waves in its physics. So the first progress I consider during the second phase, after the launch of time, is the understanding of the NO 5.3 micron and CO2 cooling 15 micron using SABRE, following the UV heating. So the left figure is from John Emmer's paper that's showing that the neutral density at 400 kilometers, which is a very just follows the solar cycle of UV, the solar UV. The right-hand side is from shows the SABRE NO power, and it also follows the same solar cycle. And also NO responds very rapidly to the energy input from geomagnetic storms, and return the thermosphere back to the cooler equilibrium. So this shows the response of NO radiation during a geomagnetic storm. You can see the hotter, the stronger NO cooling during the peak of the storm, and return it back to a quite cooler thermosphere. Another progress was on the understanding of the increasing anthropogenic greenhouse gas, and mainly the carbon dioxide, and the carbon dioxide radiative cooling that drives a cooler thermosphere, a colder thermosphere. And now, because the temperature is smaller, than the thickness of the thermosphere becomes smaller as well. So at a certain altitude, basically the observed density becomes smaller. So this is also from the Emmer's paper that shows, especially during solar minimum, the density shows a downward decreasing trend. And basically the SABRE observed the CO2, this red line, is increasing following the ground measurement of CO2 abundance of this blue line, and the ice core CO2. So it's confirms that CO2 is increasing in the upper atmosphere. And this paper by Malinczak shows, just take a look at the geopotential height thickness at about 110 kilometers. Besides the solar cycle, it also shows this similar decrease of the thickness. This is inconsistent with the 400 kilometer neutral density. I consider the second progress has been largely made by the modeling, the modelers. So one example was actually made by the HAO, that instead of coupling with the empirical DE2-based electric potential Weimar model, which has been used for decades, the new trend is to couple more realistic global MHD model like Chimera that can simulate the geoheating with more temporal variability and more spatial structures. And that gives more realistic geoheating that's during the geomagnetic storm times. So this is from, I think, from Kevin Fan's paper, showing that the MAGE certainly has more variability of geoheating and comparing to Weimar. And also the projection to the polar coordinates comparing to Weimar, which is basically a very homogeneous, following the aurora oval pattern. The actual geoheating shows more spatial structures. So I think this is a very good progress in thermosphere physics or simulations during geomagnetic storm times. In addition to the MAGE development, the Michigan also coupled SWMF MHD model one way to P10 that also lead to better resolved geoheating. Hopefully, this can be validated against by the new satellite. Yeah, so the geoheating, the more realistic geoheating leads to more realistic neutral density during storm time. So this shows the high GCM driven by Chimera or MAGE, the red line comparing to the blue line, which is Weimar, comparing to the observations of Grace neutral density. So the MAGE shows more variability and better agreement with the Grace measurement. The third progress I consider is the impact of the lower ionosphere. Not only the baseline, the mean thermosphere density or the atomic oxygen density, but also the seasonal variation of thermosphere density. I think one very important progress is the gravity wave impact on the thermosphere has been added over recent years. In the classic linear gravity wave theory, this very cold mesopause region, it's super unstable. So decades ago, a lot of people don't consider that gravity wave can penetrate this mesopause. A lot of the waves just break there or become unstable. But a contribution made by Sharon Vadas and her colleagues is they established this kind of multi-stage gravity wave generation, higher order gravity waves. So instead of in the classic Lindzen gravity wave parameterization, instead of if the wave becomes stable, they just take it out of the picture. In this new paradigm, when gravity waves dissipate, they could generate higher order secondary gravity waves or tertiary gravity waves, and they propagate into the thermosphere and take effect there. And instead of gravity wave parameterization, scientists like Hanli Liu, they just increase the resolution of the thermosphere model, like Wacom-X, and just resolve for those graduates. And this could also change the dynamics in the thermosphere. So this is from Hanli's recent paper showing the solid line is a high resolution and the dashed line is just low resolution. Not only changed the mean meridional wind and the vertical wind, it also make the O2-N2 ratio, so modulate the atomic oxygen and nitrogen abundance and make the O2-N2 ratio more realistic comparing to observations. Make it smaller. Another development is we now realize there's a wave-driven circulation in the lower thermosphere to complete the loop of the upper thermosphere, the summer to winter circulation, and the mesopause is another summer to winter circulation. And in between, there's a reversed flow from winter to summer. This was reported by Chen et al. Papers, and also Jack wrote a couple of papers to establish the theory. And this could, because atomic oxygen is photodissociated around this region and was transported by the advection or by eddy diffusion below 100 kilometers and chemically free body recombine into oxygen. And with more realistic wave forcing and resolved vertical advection, now Wacom-X can reproduce the structure of the distribution of atomic oxygen better than before. So this is the Naval Research Lab MSIS 2.0. You can see there's a sandwich pattern of atomic oxygen, and that's more comparable to Wacom-X. And in the old MSIS 0.0, it doesn't have this. The reason is because MSIS 2.0 includes new satellite observations of atomic oxygen like SABRE and OSIRIS, and others. And like I said, the major species of the thermosphere, the upper thermosphere, is atomic oxygen. So the better resolved atomic oxygen in the lower thermosphere that fundamentally change the performance of the thermosphere model. And also from the rocket measurement by Larson that shows that the wind shears peaks around 110, 100 kilometers, and above that, the wind shears is killed by large molecular diffusion, and that is inconsistent with the ICON mighty wind measurement. Shows the large wind shear exists below 150 kilometers, and this kind of very large wind shears they can cause strong mixing of species. Okay, so go back to the physics models. So there's still a long way to go in order to simulate the mass density. So this just I use 1MIPE because from NOAA SWIPSI because that's a operational ionosphere thermosphere model. So this blue curve is 1MIPE neutral density. I believe at 300 kilometers. And the red line is MSIS, and the black line is Grace FO. So this is the neutral density, and this is a ratio to Grace FO. So 1 is the best. So empirical model MSIS 0 is oscillating around 1, but 1-MIPE is about 2 to 3 times larger than the observations. So probably my message is for the physics models, because the mass density is controlled by very large variety of physics processes. Some are direct, some are indirect. So to get the mass density right, really needs to get those physics in space, in place. So the CCMC, the Goddard, the NASA Goddard Community Modeling Center, we are building this live online validation tool called CAMO for neutral density. So this is a web page. My colleague Jack is leading this effort with our software engineers. So we basically comparing the model, either physics model or empirical model, mass density to the accelerometer mass density measurement, like Grace FO, CHAMP, GOCHE. For different storms, also we're expanding it to the year-long quart-time measurement. So those are the scores. 0 is always the 1 is always the best, means the simulation equals the measurement. And we created some metrics, and it's alive. So with updated version, we always add it to the list and compare and provide unbiased evaluation. I'm almost there. So this kind of schematic that Wenbing and I came up, of course, it's based on Ray Robo's old chapter, and also the new satellite missions like timed and other satellites, along with ground-based measurements. They carried us, lead us to this point. So look into the future, hopefully dynamic would reveal more physics in the thermosphere. And the GDC could tell us more about the ionosphere, magnetosphere, thermosphere coupling. So to wrap it up, this is my view of mass density now. Because the source and the sink of atomic oxygen is in the MLT region. It's kind of like a valve. The MLT is like a valve for atomic oxygen. That's why a lot of modelers are playing the trick of KZZ, the eddy diffusion. Basically, it controls the starting point of atomic oxygen here, whether that's physical or not. And match the oxygen density with like CHAMP at a certain height. But the problem or the limitation of this trick is if the advection, the circulation, or the temperature is not realistic, the model, by just changing KZZ, it could match the mass density at one height, but it could be off for another satellite measurement. So I just want to point it out. I know this trick has been pretty much used by all the physics models. So this is my outlook, my personal outlook. Also, I think Wenbing endorsed that. an updated comprehensive review of thermosphere physics, I think it's overdue, especially considering so many satellites are launched into the thermosphere, and we really need a very accurate physics model to simulate the neutral density. In terms of satellites, we're really near the dust of the second phase after timed. And so many satellites have already ended, like ICON and AM. So can we enter the third phase, dynamic and GDC? That's a question mark. And if so, what kind of new scientific questions to really ask and to advance this community to the next level? In my view, right now, the model development is leading the observations. We can see a lot of new results, new physics actually coming out of the DRIVE CGS Center or the like Wacom X, all those high resolution Wacom X rounds and others. Can data simulation solve everything? Can just fix everything? And if so, and where's the data even for the data simulation to work? And the last part is education. So where are the next generation thermosphere physicists? Just looking back at my career, the thermosphere physics is an interdisciplinary field. It needs training in both atmospheric sciences and also physics. From my experience, like Dong introduced, I got my degree in electrical engineering, but when I was in PhD, I already finished all the courses there, in my master's and undergrad. So my advisor just advised me to just take courses in both atmospheric sciences and physics department. I think I benefit a lot from those, education part. This is the last, the Wizard of Oz, or O as a function of Z. So what controls the magic of Oz? The photochemistry, the diffusion, molecular or eddy diffusion, the advection, the circulation, including the lower atmosphere forcing, then the heating and cooling, the UV heating, NO and CO2 cooling, doing for the magnetosphere energy input, the geoheating, particle heating, and so the heat conduction to the lower part of the thermosphere. Yeah, that's all my talk, and thanks for listening. And I really appreciate all the knowledge, all the discussions I made with HAO and NCAR scientists.
Thank you, John. It's really this is a really nice talk, and I think at least myself learned a lot. It's a very great tutorial, and also I agree with you. Such a review or encyclopedia is really timely at this point. So yeah, let's go around the room. Any questions? Just in case you don't see the camera, so in the room we have Art, Henley, Jianlu, and a number of postdoc students and early career scientists, and you can see who are online. I think camera is certainly on. People can see this room, but not so clearly because it's split the cameras. But anyway, question. Hanley, please.
Hey, John. Thanks for a nice talk. I was wondering in the comparison, you were comparing the density. I think it's the density between 1 IPE Grace, Apple, and Amsterdam, right?
Right.
And what altitude is this? What's the altitude of Grace Apple? I'm very ignorant there.
Okay. Yeah, that's a good question. It's something around 500 to 600 kilometers. That's above the altitude of 1MIPE model. However, in their post-processing, they extrapolate to higher altitude using MSIS, helium, and also atomic oxygen, I think.
I see.
Yeah.
And did they look at the if this difference in densities that mainly due to temperature difference or composition or both?
I'm not sure if they looked into this, but we did send this to SWIPSI. I know they are just mainly adjusting KZZ to match the mass density, of the observed mass density.
I see. Thanks.
Yeah, I have a quick question. Yeah, you mentioned this mass density certainly is very important in many aspects, not just the physics for the thermosphere itself, but from application-wise, we know it plays a critical role in satellite drag. But right now, it looks like the data product that we use for the neutral mass density is basically from like accelerometer or I'm not sure if any other techniques have been used. So do you know any information about the upcoming GDC or dynamic? How will that deal with the density? Yeah.
Right. Dynamic is still, there are different phase A proposals. I can comment on that. For GDC, I know there would be mass spectrometer to measure like atomic oxygen and other species. So it would be more like the DE2 type of measurement that MSIS uses. I'm pretty sure there will be no accelerometer on GDC.
Okay.
Yeah, but if you know the density of atomic oxygen and like nitrogen, then the mass density can be calculated.
Yeah.
Okay, Xian has a question.
Very nice talk, John. I have a question on your last slide, 31. This might be an easy question. So you mentioned different heating and cooling processes. So I wonder whether so these cooling and heating processes affect all. Is it more like causing the upwelling, downwelling, or it's more like changing, for example, temperature, then reaction rates, then the chemical processes? So do you have any comments, for example, for different heating and cooling processes, which one might be more important in GMO?
Yeah, this is a very good question. I could be wrong because I didn't investigate into this. My impression is it's less important for photochemistry rate, the reaction rate. I think the models and they are using the fixed rates, but it's more important for I think first of all just expansion, the ideal gas law, and also the heating and the cooling, especially the heating, that drives different circulation patterns in the thermosphere and change the composition. So I think to address your question, probably dynamics is more important than chemistry.
Thank you.
Thank you.
Okay. Do people online have any question for Jia?
Yeah, I have a question. Jia, nice talk. When you're at the CCMC, do you do any validation of the models at all, or you just run the model?
Yeah. Well, this is the validation part.
This is the validation part.
Yeah. So we're doing a very comprehensive validation of neutral density against the accelerometer data.
You have a result. Which one's better? Which one's not good?
Yeah. If you go to this link, you could play with it. In general, empirical models are much better. Then that if we just compare with the physics models, my impression is high GCM is better. We haven't published a paper yet, but that's kind of my impression. Like this, the list of this storm list is not even complete. We will have about like 100 geometric storms during the Chen-Gaucher grace period, and then the statistics will have the average ratio and also standard deviation. Yeah, so this is basically the validation. And also CCMC is led by Mingyang Zhou, is leading the validation against ionosphere data.
I see. I saw Astrid has raised her hand. Astrid, please unmute yourself.
Yeah, thanks. Very nice talk, Jia. With respect to the validation, I mean, what is your main focus? Is it the absolute density or the variation? Is it specific scale sizes? I mean, is it more validating the model, or is the focus more, something satellite operators could then use to know how models behave?
Yeah, it's a very good question. Actually, both. So for this camel, we actually normalize the density against the pre-storm quiet time. So for this case, we're looking at the change of neutral density during geometric storms. And the next version, we're looking at like the whole year. So that would be the absolute neutral density. The question about the users, yeah, that's how users gonna looking at this. I don't know. We're not facing the users like Noah Swiftsy does.
Yeah, thanks a lot. I mean, if they know there is a bias, or I think they need to know the variation. And with respect to the WEM IP, I mean, you probably know there is continuous in the test bed plots comparing the model which runs in operation, the real time, as well as the prediction is compared to MSIS.
Yeah.
And that is provided to, interested operators since a lot of them are still using MSIS.
Yeah, I think MSIS 00 is not accurate. The MSIS 2.0 is much better. I think the issue is it cannot be used commercially. So if just comparing to I know a lot of the new models are just comparing to M600, but that's not the state of the art. Like DTM 2020 is also much better than M600.
Okay, thank you.
Yeah.
But yeah, I think this kind of validation certainly will be very useful if you can give those feedback to each of those model development team. And yeah, since you mentioned you will be working on such a paper, I guess those developers may be involved. So hopefully that will help the community to have better models overall.
Yeah, that's I think that's the point of this kind of online tool. It's not a paper. Like all the previous validation papers, once they are published, that's the end, right? And for this online tool, we keep adding the new versions of model. So like keep track of the progress of model. So it's kind of alive.
Okay. Oh, last question, Valerie Beauty, please unmute yourself.
Yeah, just quick question. Are you planning first, thank you for nice talk. Are you planning to do comparison with Camel for Superstorm? May?
Yeah. It's we're running the models at the CCMC right now.
Yeah. Any preliminary results? How basically models disagree to each other? Big spread or just?
Yeah. Well, I haven't seen the results.
All right. Thank you.
Yeah.
Okay. Well, I think we have passed the hour, and thanks again, Ja, for giving a really nice talk. And we hope you can visit us sometime in the future in person.
Yeah. Thanks for the opportunity for the communication. Yeah.
Okay. Thank you. Thanks for speaking again.
Thank you. Bye.
Thank you. Bye.